So this next session, we thought we'd spend a little time looking at Jupyter and which I'm assuming you've covered a little bit this week, or maybe you'll see more about it later in the week. But in terms of how it relates to visualization, we've got 3 presentations we're going to have for the remainder of the day, and we're going to start it off with Tommy.
All right, great, thank you. Hi, everybody. My name is Tommy Marrinan. I'm a professor at the University of St. Thomas up in Minnesota with a joint appointment as a computer scientist at Argonne. So I'm just going to kind of go over with some work that I've been doing with a student intern this summer, Pam. So a little shout out to her because she's contributed significantly to this. And this is kind of about how can we use these interactive Jupyter notebooks, which are great for kind of testing and developing code. How can we use that to interface with kind of high performance computing clusters to do really large scale work with these nice, convenient, interactive front ends. So first, we just kind of created this little documentation on how to set up or configure Jupyter notebooks on an ALCF resource like Cooley. One of the really nice things about Cooley is that every single node has external internet connections, so we can actually host a Jupyter notebook on any node on Cooley and connect to it from your own local machine. And so that is kind of one of the nice things going on there. I won't go into the super specifics of this, but this is just kind of a documentation for people looking to do that here. All right, so some of this stuff will kind of look maybe a little bit fun or silly, but trust me, it has a payoff at the end, and it's kind of building up the pieces as we go. So first thing is most people use Jupyter notebooks with Python, but there are kind of different plugins that let you use different languages. And one of them is C++. And this is kind of was a big effort because C++ is a compiled language, whereas to do these things interactively, you need it to be interpreted. So this took a brand new kind of converting a compiler into an interpreter. So it's a little bit of a work in progress, and there's been some bumps, but it's gotten pretty well flushed out at this stage, and I expect it to only get better. One of the big benefits of doing things in Jupyter notebooks is that your output is not just limited to text-based output. Normally when we run programs on a command line interface on a supercomputer, there's no display connected to it. You're just going to get text-based output there. But we can do images. So I just want to take a moment and show how we can kind of create these in memory, just these arrays of raw red, green, blue, alpha images, and actually display them on the web page. So here I've just created a very simple function for manually filling in an 8x8 pixel array with a yellow smiley face, and a second one that just kind of does some stripes. It kind of looks like a flag. It uses the ANL logo colors. And what I can do is just go to each cell and run it. So this first one is just importing the necessary libraries. Then I define the function for filling a pixel array with the smiley face pixel values. Another one for the stripes. But then the real, what we're really going to be looking at here is the main program. And what this is going to do is display each of those 2 images alternating every 2 seconds. And the nice thing here is I'm not going to be spitting out a new image each time and see this whole big long list of images. I'm actually going to update the same image. And this is useful because then we can kind of play an animation, which we'll see a little bit later. So taking a look at the code, I'm basically allocating the array of pixels, populating that array with the smiley face values, creating this image, which is specific to only interface with Jupyter notebooks, so you can't take this code kind of out of Jupyter notebooks and have it work. Giving it a unique ID so that I can later replace the contents of that same image instead of creating a separate one and then displaying it, showing it in the notebook. Then I'm going to loop 10 times, and every 2 seconds on every alternate iteration, I'm going to replace the pixels with the stripes for the smiley face, update the image, and then reshow it. So let's go ahead and run this. And there you go. You see the smiley face, and then the kind of flag, and then the smiley face, and then the flag, and it'll do this 10 times. All right, and I think, there we go. Okay, so that's just kind of highlights, the ability to output data that's not just limited to text-based outputs. All right, so how can we use that for kind of, simulation science? This here is a notebook that incorporates kind of a really nice two-dimensional fluid flow simulation. It's a lattice-Boltzmann methods is the kind of the simulation technique behind it. It's just two-dimensional. I can pull up the code. You'll notice that it includes 0 external libraries other than a math library for doing like square roots. So it's all self-contained, and I'm not really going to go into what the code does other than to highlight that it is under 400 lines of code. So this is kind of a nice simple thing to do a fluid flow simulation, but this, for demonstration purposes, it's also nice for people kind of getting into this for the first time. It's digestible. You don't need to know a million other kind of external tools or libraries or things like that.
Hey, Tommy.
Yes.
Sorry to interrupt. Can you increase your font size a little bit?
Sure. Better or more?
A little more.
Keep going.
It's hard to, I think some of it may just be latency with the video because it's sort of pixelated at times.
Okay.
Maybe what, but increase maybe one more time. That's much better.
Yeah,
Okay.
much better.
Sorry about that.
Thanks.
Okay. So what we're going to do here is this simulation is going to be a two-dimensional fluid flow simulation that is basically we've got, I think in this simulation, it's corn syrup flowing through a pipe from left to right. And in the middle of the pipe, there's this kind of barrier or blockade. And what we're going to be looking at is the vorticity. So how this causes kind of turbulence that spirals in the fluid flow. And what we want to do is not just look at a bunch of raw numbers, we're going to want to visualize it. So we're going to use what I just showed with that smiley face and flag, but we're going to now take every single step of, or not every single step, but every few steps, we're going to output and compute this vorticity, apply a color map to the vorticity, and actually show it. And we're going to see kind of the simulation animating in front of us as it's computing. You've heard a bit about in situ kind of visualization and analysis, throughout. So this is kind of that again, but using Jupyter notebooks. So here we're just defining a function that takes that scalar array. So we've got an array of vorticity values. Those are floating point values, and we're going to convert it to a red, green, blue, alpha pixel array. So let's go ahead and run that. This is setting up the fluid simulation properties. So in this case, I'm going to keep a pretty small scale for demonstration purposes, 400 cells wide, 160 cells tall. We're going to compute 5,600 time steps. We're interested in the vorticity. We're setting up, where the barrier is. So that's something that's kind of hard coded in there. And then we're setting up all these physical properties of our fluid and boundary conditions and stuff like that. So what is the density, the speed that it's flowing, what's the viscosity of our fluid, all sorts of stuff like that. So let's go ahead and run that, and we output some statistics about it. Then we're going to go ahead and initialize that lattice-Boltzmann methods simulation. We're going to create our color map. This is what's going to translate those vorticity values into red, green, blue, and alpha. This is going to be a divergent blue to white for the first half and white to red for the second half. So we can really see the counterclockwise vorticities and the clockwise vorticities. And finally, we're going to run our simulation, n time steps. And so again, we're going to be creating initially this grid of pixels that's all white and displaying it. Then we're going to run our simulation, and every so often, we're going to compute the vorticity, convert the vorticity to that pixel based on that divergent blue to white to red color map, update the image and redisplay it. And then we're going to do on every time step the actual simulation itself, which for lattice-Boltzmann methods, again, maybe not super important, but it does some sort of particle collision and streaming, as well as this bounce back stream, which is when things hit the barrier and kind of go back the other direction. So let's go ahead and run this. And here we go. So now we see not just kind of data being output, but as it's computing, we can see the results of the simulation, and you see these vortices forming, the blue ones being our clockwise rotations and the red ones being our counterclockwise rotations. And one thing I want to point out is, even though this is pretty small scale, 400 cells by 160 cells, it's still kind of a little bit choppy. Maybe you thought this video was just choppy because it's over Zoom, but even for me, it's a little bit choppy, right? We're only getting, maybe 4 outputs per second or something like that. All right, and there we go. It has finished. So this was all run on a single node, right? On a single process. Nothing parallel about this so far. So nothing kind of too crazy going on here. This is your typical Jupyter Notebook setup. You write some code. It has some output that's text-based and other output that is a bit more rich media. But it's all kind of just running here locally. So let's take a look at how we can use MPI. I know there was a session on MPI. I don't know if everybody attended that or how familiar people are with that, but this lets you run code across many nodes of a cluster. And that's kind of typically something that Jupyter isn't necessarily built to do. But one of the really cool things with this C++ plugin is it lets you actually swap out the interpreter for interpreting your code as you write it for a real compiler, and it lets you take the code that you've written in the notebook and compile an actual executable that can then be run. So let's take a look how this might work for creating an MPI-based application. This is just a hello world. So first thing, we have to tell Jupyter where MPI is installed. So we're telling it where the include directories are, where the libraries are located, and then linking in the MPI library. The main application I'm going to run is just this hello world. I'm going to get the host name of the node that each process is running on, as well as kind of its rank, which tells us kind of which, the ID of which process this is out of n total processes. And then I'm just going to print that out. Then I have this magic command here. If I start with executable, this is basically going to put the following cell inside C++'s main function and actually create an executable. And afterwards, I have my kind of library linking instructions and stuff like that. That's going to be copied directly from whatever MPI tells you it needs. So here I initialize MPI. I call my MPI hello function, and then I finalize MPI. So I don't think I actually was running these cells. So run that one. run that one. Now I'm going to run this one. And you'll see that it says writing executable MPI hello. So that's the name of the executable that was actually written. If I go onto the file system on Cooley, I will actually see this. I could actually run this outside of Jupyter altogether. It's a compiled executable that can be run anywhere I want. Next, kind of another magic. If I start the next line with an exclamation point, it's going to run an executable. But instead of running this executable directly, I'm going to launch it with MPI. And we launch it. And there it goes. So it's a little bit jumbled here. So one thing about doing kind of parallel or distributed computing is all these things are running at once, and I have no guarantee which is going to run first, right? But we can kind of make some sense out of this. But let me go and uncomment this code I'd had commented before. And what this is going to do, oops, is now it's going to make these print statements print out in order. So first rank 0 will print, then rank 1 will print, then rank 2 will print, etc. All I need to do is rerun these cells, recompile the executable, and rerun. And now it should look a little bit easier to read, right? Rank 0 out of 4, hello from host, this is Cooley node 13. Rank 1 is on Cooley node 1. Rank 2 is on Cooley node 6. And rank 3 is on Cooley node 8. So you can see this successfully launched and was executed on multiple nodes of the Cooley cluster. So that's pretty exciting. Now I can write my code here in a notebook interactively. I can compile it to an executable. I can execute it on many nodes of a cluster, and I can get the data all back into my notebook here to kind of view. Okay, next step. Again, this will look a little bit like a toy example, but using that exclamation point way of launching MPI, or any command for that matter, it will automatically print the output in my notebook. What if I don't want to print the output? What if I want to use that for some further computation? So here we developed some code, a class that allows you to launch a process and store the result in a string, so that instead of just showing it, it's now stored in a string, and we can use it for further processing. And to demonstrate this, I am going to use image magic, which is kind of like a command line based Photoshop. So there's no graphical components whatsoever. You just on the command line kind of type in whichever filters you want to apply to an image. I'm going to use image magic to read a JPEG of Argonne's logo, convert it to raw RGBA, and then instead of saving that as another file, it's going to output it to standard out. In other words, it's going to print it. But instead of printing and showing here in my notebook, I am going to save it as a string. And then I can take the contents of that string, convert it to just a byte array, and use that as the image to kind of display here in the page. So here, run the includes, run the process spawning, and there it is. We have Argonne's logo. This was read in by an external program. The output of that external program was saved in a string in our notebook, and the contents of that string were then used to kind of display an image here. Okay, final notebook that I'm going to kind of go through. Let's put it all together. We've got the simulation, we've got the image displaying, and we've got MPI. So let's take all three of those things and put them together. First part of this notebook is going to be writing the MPI program. So this is going to be our simulation, but this time instead of running serially, this implementation of the Lattice-Boltzmann method simulation has been written for distributed computing using MPI. So here I've got my function to kind of run the CFD simulation. It's going to set up those same properties that we saw in the serial version. But one thing I'm going to point out here is that I am actually going to print out what the barrier looks like, and I am going to print out on every single output what the vorticity values are as raw binary data. I'm going to actually write it out onto standard out. Now, if we were to actually write this to standard out in a normal kind of terminal situation, this would look like pretty much garbage filling up your terminal. But again, this is going to be launched from another piece of code and stored in a string. So we're never going to see this on the standard out. It's going to be kind of piped into another piece of the program, if you will. So let's go ahead and run that. Again, we're going to go ahead and create our executable. And this is just going to initialize MPI, run the simulation, and then finalize it. All right, so now we can kind of stop there. And this is part 2 of our notebook. This is going to interactively run the MPI program that we just compiled and visualize it. So again, we've got this scalar array to RGBA. This is going to take those vorticity values that are being output to standard out and convert them, given a color map, to some image. So let's go ahead and run these two. The color map again is going to be that blue to white, white to red. And now the process that I'm going to launch is MPI exec. And let's do 8 processes this time. And we're going to run that program that we just compiled. So this is the exact same situation that we had before, except now we're going to do parallel processing for this simulation using 8 different processes. So it should go faster. Remember, last time we saw it and it kind of chunked along a little bit. This time, hopefully we'll see it a little smoother as long as Zoom can keep up. What we're going to do then is read the output of this process being executed, read the standard output until we get these kind of markers of where each output time step begins. So we're going to, if we begin barrier, begin output, which again, if I scroll up, we're just kind of matching keys that the program itself was printing. Otherwise, this is going to look the same. I am going to create the image, display the image, continually read standard out as long as its output is the size that I'm expecting. So basically until the end. And then I'm going to close the executable that I opened. So let's go ahead and run that. And now hopefully you see this running much smoother, much faster. And it's already done. So this was still at really small scale, right? I did 400 by 160, but you can quite easily imagine, wanting to run this at much, much larger scales that would be prohibitively slow on a single core, doing it in serial, and this being a way to do it in parallel. Another thing that I want to mention about this framework, if you will, or this workflow, is that nothing special was needed in the simulation. All that was needed, you didn't need some big third-party library to stream data between it and the Jupyter Notebook. All that we needed was to print data to standard output in order to be able to kind of read it back in and put it to use for some other purpose. So this is kind of the final picture here of doing in situ visualization of large scale, distributed simulations using Jupyter Notebooks.
Thanks, Tommy. Any questions for Tommy? Other than I see there was one in the chat asking if you can essentially make your code available.
Yes, I think I can. It's currently on a Git repository that's hosted kind of internally on Argonne's. I don't know. I think currently it's got private settings, but I'm more than happy to make it public if that's something.
Is it possible to just tar it up, zip it up and put it? There's a box folder for today's thing.
Yeah,
today's
I can do
session.
that.
So Tommy, there's another question on Slack, and it's about clarifying on how Jupyter interacts with the Cooley job system, right? With the scheduler.
Yep. So what I did was I just went logged into Cooley like I normally would, grabbed an interactive session with however many nodes I wanted. I think in this case I asked for 4, and then once I got on Cooley, I just launched Jupyter Notebooks, and whichever, I had asked for 4 nodes. You typically are given a login shell onto one of those 4. So whichever one I actually launched Jupyter on, that's what matched the URL. I don't know if anybody noticed the URL in the browser window that I'd shown, but that matched the one of the 4. Yes, it was CC013 was the one that I had launched it on.
Also, your Jupyter server is running on the head node.
It is running on whichever node I am given by the submission system.
Yes,
Right.
And I could choose any one I want, right? There's nothing stopping me, even if it put me on CC 013, there's nothing stopping me from SSHing into any one of the other nodes that I am given in my allocation and launching it on that one.
Yeah. Well, I think that clarifies the question.
I see another question here in the chat about the C++ capability. Yeah, that is a plugin. It is called Zeus Cling. I'll put that here. That is kind of the project for taking C++. I think it was taking Clang and making it an interpreter version of Clang, the C compiler, C++ compiler, and making it an interpreter version that then